Afternoon. As you heard, I'm between you and a coffee, so I'll try and run at a similar pace to some of the other people today and try and keep it to the 25 minutes. My time has started, but I'll get looks off James if I'm not. My name's Paul Gledhill. I'm a lead engineer at Lloyds Banking Group, and I'm focused with my team on trying to bring serverless components into Lloyds Bank. What I'm going to cover today is I'm going to focus on my favourite Google service, Cloud Run. I don't think enough people know about it, so I'm going to talk about it quite a lot. But I will start with Cloud Functions, give you a bit of a view in terms of where that fits in the landscape, then come back to Cloud Run, do a bit of a deep dive on both. I might even throw some GPU stuff in there at the end. So, Cloud Functions. What is Cloud Functions? So Cloud Functions is Google's Functions as a Service offering. So this is one of those where you bring your code, and you let them kind of handle everything else. So you bring your code, pass it across. There you go. Pass some code into Cloud Functions. It does some magic, and then you get a HTTP endpoint that consumers can call into to invoke that code. Okay. Little sniff test here. Is it serverless? My definition of this is that it has no infrastructure management. You're not dealing with the kind of the virtual machines that sit underneath here and the kind of how much memory and hard disk space that those machines have got. Automatically scales. So as load comes in, Google will actually scale the instances behind the scenes to meet that demand. Pay per value. I like Jan's graph earlier in terms of, if there's no requests coming in, I don't really want to have to be paying for this thing. And as more requests come in, I don't mind starting to pay in a relatively straight manner for that. And highly available. I don't tell Google where to put these functions other than in a particular region. They'll make sure that it's across different zones. If a zone fails, they'll make sure that they spin up more instances in the other zones and make sure that it continues to respond to consumer requests. Okay, so that's kind of what it looks like. When we start to use this and we start to dig under the covers a little bit, because you can imagine it's the kind of service that developers all want. They want something like Lambda. They've heard of Lambda. We found that actually Google are quite transparent about how they do that magic of changing it from some source code into something that runs on an execution engine. So they take your source code and they pass it across to their CI/CD pipeline tool, Cloud Build. Cloud Build then runs a build pipeline, generate a container image, pushes the container image into artifact registry, a little bit like Docker Hub, and then when the Cloud Functions runtime kicks in, it's going to grab that container image out of the artifact registry, and it's going to invoke the function that you've done it. Okay, fine so far. So let's dig in a little bit more. They even show you the logs, so you can go into Cloud Build, you can see the logs for that build process. 3 steps. Fetch, it's kind of grabbing the code from somewhere. Not quite sure why they need a middle one, which does some kind of configuration. And then the third one is where it builds the container. Okay? So let's dig a little bit deeper. Let's kind of get into the YAML that sits behind this. And when you get into the YAML, you find out there's only really one main build phase as part of this process. And that is to call pack. I've not really come across pack before, so I did a little bit more Googling. And it's a cloud-native build pack. So cloud-native build packs is something that came out of Heroku, and then in partnership with Pivotal kind of formed it into a proper open source project. And the purpose of the project is to allow people, whether it's in the cloud or actually on your local machines, to just bring some code, not worry too much about having to build a Docker file that's going to create the container image, and just generate that container image. And there's a whole set of different coding languages that they support. Okay, so I install pack on my Mac, and I run pack build suggest, and it comes out with a whole set of different build packs that might kind of work for the code that I've got. So you've got some by Heroku, you've got these Paketo build packs, and then you've got a set of Google build packs. That's great. So how would this actually work to build a container image on my machine? Well, you just do pack builds. You pass it in the name of the image you want to create, you pass it in the path where your code is, and you give it the builder. I haven't told it what I want it to build in terms of what the source is. So as part of this build pack process, you actually find that the build pack's going to interrogate your folder, They look at the files, they look to see if you've got requirements.txt, they try and work out, is it nasty Python? Is it something a bit nicer like Go? And they'll go away and it'll build that image. Google being Google, you can actually even go and have a little look in GitHub and you can look at the source code for the builders, which is kind of cool. I found a bug in one of these because their Python one didn't deal very nicely with white space. So it would work using pip install, but if your requirements.txt had too much white space in, it wouldn't work. But I managed to find a little line item. I think I sent a ticket. I don't think they did anything with it, but I was quite pleased that I'd kind of managed to get there. Okay. So here we are, quite like Cloud Functions, and we can kind of see how they've pulled this together in terms of their kind of components. So, at the moment, I'm feeling quite good about it. So here we go. I've got a repo. I pass the code into Cloud Functions, pass it into Cloud Build, and it generates a container image, and it's a nice little kind of cube with blue colors on it. And then I get into my test environment. It's a different project because I want to keep a bit of segregation. So again, I take my code, and it's the same commit ID. It's exactly the same code. Pass it into Cloud Functions, pass it into Cloud Builds. It's a slightly different image that gets put into Artifact Registry. Doesn't feel too comfortable. And then in production, so I've got a production account. So I've still got exactly the same source code, passing it into Cloud Functions in production. It's using Cloud Build to generate the container image, and it's a slightly different image again. And this is because you can't specify exactly what version of that build pack you want it to use, and they release versions every 2 weeks. And obviously, as part of a build process, you go in and you're grabbing all of your dependencies. Unless you've done a bloody good job of pinning down to like the version, you're probably going to end up with a slightly different image. So I work for a bank now, but my heritage is kind of online banking. I used to be on call. I would not want to get called out at 2 o'clock in the morning if there's an issue and not hand on heart say that what is in production is what we did in testing. I would just hate that. I mean, you also can't go back because, you can't force it to do this thing. AWS, by the way, with Lambda, you can actually pin to a runtime image, so they kind of get around it using that. So I like Cloud Functions, but I didn't like this aspect of it. The other bit is, you saw the pipeline. I mean, it was 3 stages, but it's really only one, it just builds. If people work in an enterprise, that's probably not what your build pipeline looks like. You've probably got a little bit of, secret scanning in there, a bit of static code analysis. You're probably going to check that the format of it's right, that it meets your company standards for what, variable names should be and all that kind of stuff. There might be some license compliance or security compliance on the dependencies that you're pulling in. You want to do all of these things. You don't really want to allow people to do all of this and then generate an image and then have to almost reverse engineer it. And you also don't want to have to put a process in place for them to, before Cloud Functions, it just doesn't feel quite right. So I like Cloud Functions, but it's got some areas in there that I don't think are very enterprise compatible. Okay. And then when you dig a little bit more, and this is with their latest version of it, you find that the engine that they use to run these container images is actually a thing called Cloud Run. So actually, Cloud Functions is just a pipeline to generate container images from source code and then just pass it to Cloud Run. And I've given similar talks for quite a while, and then Google released a naming change. It isn't actually called Cloud Functions with a capital F anymore. It's now called Cloud Run Functions with a lowercase f. So they've kind of acknowledged the fact that this is really just part of the Cloud Run ecosystem. But I haven't really told you what Cloud Run is yet. So Cloud Run is a container as a service offering. You don't bring code, you bring a container image. You can build that container image anywhere. And I really like this because this means that in my company, we can build an image that we're going to put into Kubernetes or into Cloud Run or maybe on-premise. Maybe we've got an on-premise Red Hat solution. You can build it in any way you want, just as long as you then push it into Artifact Registry for Cloud Run to pick it up. It also means that I can confirm that that image is exactly the same image that is being used in testing and dev and prod. So it kind of, lets me sleep at night when I'm on call. Okay. Is it serverless? Still no infrastructure management. We'll get into how you configure it, but you don't worry about the machines that are sat under it. processing this. Automatic scaling, as more load comes in, Google will just scale the number of container instances up. Pay per value, if you don't call it, you don't get charged. And then there's a call-in, there's a charging model that's based on the number of calls or instances. And it's highly available. They worry about where they're going to be placing these instances when they're running. Okay. So, how does it work? Similar to some of the platforms, when it's not running, they don't have it sat there ready for invocations. When the very first request comes in, there's a bit of a period at the beginning where it's starting up, kind of starting up your container image. Paul talked about the kind of cold starts and the different languages and how they, and I'll dig into that in a bit as well, but depending on your container image, it might take quite a while for that to start up. Then it's serving requests. This is the bit that they charge you for. So they're going to charge you whilst it's actually serving requests, and it can serve multiple concurrent requests at once. As soon as the last request that it's processing has been complete, they put it into an idle state. So this is where it's warm. It's ready to handle more requests, but they lower the CPU right down, and they don't charge you for this bit, which is kind of nice. They'll keep it in that idle state for a while. One more request comes in. They'll put it back into the hot state, process your requests, back into idle, and then after it's been idle for up to 15 minutes, they'll shut those instances down. Okay. What else can you change? Obviously CPU and memory, small amounts of memory, fractional memory, all the way up to CPU, all the way up to about 8 CPUs, memory, 128 meg, all the way up to 32 gig, fine. Instances. So by default, they'll set it at 0 instances that are running all the time, with the maximum instances that can run of 100. So all of those boxes could kind of fill out with running instances. The reason I mention a minimum is that you can actually set a little value, and they'll keep them warm all the time. So they'll keep them running. They'll charge you for it, but they'll keep them running all the time. And that just alleviates that issue, potential issue, with cold starts. Okay? What I like about this is, in production, you could have it with a minimum, and in dev and test, you don't. So in your dev and test systems, you're not going to be paying anything when calls aren't coming in and you're not testing the system. By default, the quota says that you're allowed up to 1,000 instances that it'll scale up to, and there's a broadcasting corporation across the way somewhere that have got one of their services configured with 15,000 container instances that it can scale up to. From nothing, it will go fill all of these boxes up, they finish processing the requests, it will scale all the way back down again. Okay, I'll talk concurrency. So each one of those boxes can't just handle one request at once. By default, it's set to, each box is set to handle 80 concurrent requests. It probably wouldn't. They do monitor the CPU, and once the service gets warm, it will then start spinning more and more up, but that is the value of the maximum. Or you can force it to just have it so that each instance handles one request. A little thing called startup boost. You can also tweak a little setting. So first 10 seconds of your container running, it'll double the amount of CPU, and then it'll spin it back down to a flat level. So that's a really nice way of it, kind of trying to reduce, again, that cold start time. Leads me on nicely. Cold starts. What else can we do around cold starts? I can talk about this for about half an hour. I don't think I'd be allowed. So briefly, as I mentioned, this is around how when they're kind of spinning up. I ran some .NET container. The hey command at the top is 200 requests with a concurrency of 10. And you'll see that 10 of them were around 3 seconds in terms of the cold start. And then after that, it was processing the requests in about 300 milliseconds. If you press refresh, 5 seconds later, then that time really, really drops. So each request then can be processed in like 3 milliseconds. And these, 26 milliseconds. And these are requests that are doing a small amount. I think I had them doing a little bit of cryptography, calling out to a pub subservice, putting an item on a queue, and then coming back. So they're not just doing hello world, they're doing a little bit of something. Okay. Different languages. Different coding languages have different kind of characteristics. I've shown a few here. So you can see where the kind of the cold start time is for some of these languages. You've got things like, I don't know, .NET, you know, about 3 seconds. Things like Node.js, Python, a couple of seconds perhaps. Go around about, I think it's just under 1 second. You then hit with Java. Java with no libraries and no frameworks was taking about 4 or 5 seconds to spin up. If you had a small, lightweight framework, it was taking about 6 seconds. If you had Spring Boot, it was taking about 15 seconds. And this really is doing a small amount of cryptography and sending off a HTTP request. But you will see that once it's warm, it really starts to speed up. It's you know, all of the languages are pretty good at them responding. Graal VM, I played around this a little bit. So this is the new opportunity to actually take something that would normally run on a JVM, and a lot of the stuff happens at startup time. And it's a process that then compiles that down to binaries. I don't fully understand how it works. It's quite clever. But you can see that it really helps with the cold start, and actually it does help with the execution time as well. But there are some peculiarities with Graal VM, but worth playing with. I couldn't get Rust working, so I haven't added Rust. I'm sure Rust would just be like a black line with zero startup time, and you know, like you know, infinite requests per second going through. Okay. I mean, I'm already sold on Cloud Run, but I'm assuming some people might want a little bit more. In August last year, Google made me really happy, something I could brag about. They said that they were going to start allowing these serverless containers to have GPUs attached to them. And I get really quite excited about this because GPUs are really expensive. And you have to attach them either to compute instances or to compute instances that are part of a Kubernetes cluster in Google. And that kind of process takes a bit of time, and then you might need to reserve some of the GPUs. And then the GPU, like all Kubernetes clusters, has anyone got a Kubernetes cluster that is 100% efficient? Right, no. So it's turned off. Yeah, thank you for that. So you're not really going to have workloads running against those GPUs all the time. You know, like anything, you're going to have quite spiky stuff. So I think, for me, I think this is pretty transformational. It's currently in public preview. You need to request to get a quota added to your account, but anyone can ask. You just tick a tick box in the console to get a GPU against your container. And then this is a really, really, really complicated Docker image. So it's just using, so Alarma, I'm still quite new to this AI stuff. Alarma's like a model server. And so what this container image is it's the Alarma model server, and then you can pass in the name of the model that you want it to use. And I've passed into this one either Gemma, Llama 3, or DeepSeek, if people have heard of DeepSeek. And what it'll do is when it's building the container image, it'll go out and it'll grab that, all of the weightings. It's about a 5 gig file, depending on the model you've chosen. About a 5 gig file it's going to pull into the container image. And then it just runs, right? And you can see the GPU memory, and you can see the GPU usage, and you just start getting all of the responses that you would expect from an LLM. Okay, so a couple of bits around that. Yeah, public preview, you need to get a quota allocated, fully managed, no kind of drivers you have to play around with, or, you know, Google have kind of done all of the work there. It scales all the way to 0. There's a little caveat with that, in the fact that, you know, that idle time I talked about, where you weren't getting charged? With GPUs, you do get charged for that idle time. So if you put one request against one of these instances, you might get charged for 15 minutes worth of usage if you don't use it again. I think that's just because of the way GPUs are and the fact you have to load a lot of stuff into memory. They might play around with that over time. But it's only just under $1 an hour for a GPU. Again, I think it's quite a nice price point to start playing with. Caveat, not all GPUs are the same. So the GPU that they allow you to use as part of this is an L4, which has 20 gigabytes of memory. The ones that people kind of camp on and they kind of try and grab and keep hold of, and they use for weeks on end to do machine learning, are the ones that you can attach to the compute instances that have like 140 gig of memory. So it's not one of those huge instances. It's not really meant for it's not really meant for like learning, training the model. It's more meant for inference. So where you're asking it questions and it's instantly responding. Okay. There be dragons. So I'd done some slides around costs, and it was a whole load of numbers, and I thought at this point in the afternoon you could probably do without it. But when would you use GKE and when would you use Cloud Run? And I don't want to spoil your talk later, Grace. Sorry. I'm going to say it depends. You need to look at your use cases. The kind of figures I've done are if you've got a fully efficient Kubernetes cluster versus Cloud Run running all the time, then Cloud Run's going to cost about twice as much money. But you're never going to have a fully efficient Kubernetes cluster. You're always going to have unused space as you've got different nodes and clusters and things around the place. I think it can be used for quite a lot of use cases, but you're going to have to look and see if any of those work for you. Now, I did 2 thank you pages. I'm going to come back to it because I'm just going to spend 2 minutes. So, little plug for the Northwest Cloud community. One is I help organise 2 cloud communities in the Northwest. One is the Liverpool AWS user group, and we've got some of the organisers in kind of over there. And we're running an observability workshop next week. Really keen to kind of get engineers engineering and trying things out. Look up on Meetup and you'll find it. The other one is that later on in the year, follow me on LinkedIn, and I'm sure I'll spam this one, but I kind of want to get people building stuff with AI, because I think it's really quite quick and easy to get up and running with it. And I just think we need to support people in terms of being curious. So I'm going to be running some of those events. I guess I should probably also plug the AWS Manchester group as well, because there's always some really good talks there. Okay. Thank you very much for your time. And come and ask me some questions later on if you would like to. Thank you.